So those of you who were attentive at looking at the last video, you would have recognized a mistake, and I'm going to correct that right here. I just had a little typographical error. Alright, so the next topic is combinations. So this is section 1.4.2 of Wessel. And I'm going to return back to our diagram of our dice here. And let me go ahead and erase all this. And what we just derived was how to get the total number of permutations of two successes, or two rolls of 6 out of a total of 4 dice. And one thing you'll notice is that we got some redundant answers. So in one case we had, for example, we had the yellow dice was our first roll, and that gave us a success. And then in this lower case, the first roll was on the blue dice, or the first success was on the blue dice. So you can see that if order matters, if the order in which we roll the dice matters, then we get 2 different answers. But if the order doesn't matter, then we have to take that into account. So combinations, so the number of combinations is the number of permutations when the order doesn't matter. So how do we correct for that? So in this case, there are exactly 2 redundant permutations with our two sixes, or 2 successes. So we derived NPR, and we have to divide that by the number of redundant permutations. And in this case it was 2. So how do we figure out the number of redundant permutations, for example, for R successes? So we have to ask the question, how many permutations of R successes can we have? That is, how many permutations of R out of R successes can we have? And the answer to that is R factorial over R minus R factorial, and that's equal to R factorial over 0 factorial, and 0 factorial is defined by 1, so that gives us R factorial. So the number of combinations is NCR, and that's equal to N factorial over N minus R factorial. That was NPR, that's the number of permutations. Now we have to divide by the number of ways in which we can arrange our successes. And that is our number of unique combinations of our successes. And the other I wanted to let you know also that this symbol, or that equation, describes our binomial coefficients. And we'll talk about those soon. I need to add another bar under my equal sign because this is what defines this symbol here, this parentheses with the n over r. Now for a couple of quick examples, let's say we're tossing 3 coins, and we'd like to know how many ways we can get one head out of a toss of 3 coins. And the answer there is 3 over 1, and that's 3 factorial over 1 factorial times 2 factorial, and that's 3, right? The head could appear on the penny, the nickel, or the dime. The last simple example, let's just consider 3 heads out of 5 coins. How many ways can we get 3 heads out of 5 coin tosses? And that's 5 over 2. That's 5 factorial, not 3 factorial. R is 2 factorial, and 5 minus 2 is 3 factorial. And that's, we could just write these out. And we can cancel out some terms, and we're left with 4 times 5 over 2, and that's equal to 10. So there are 10 ways of getting 2 heads out of a roll of 5 dice. 2 heads out of a toss of 5 coins. Let's now look at probability. So the basic concept is that if there are n possibilities and s of them are successes, they have some property that we consider them, that make them a success, then the probability of success is what? Okay, the probability of success is just s divided by n. If we were to pick randomly, or from n possibilities, we would have a s over n chance of getting a success. So what is the probability of drawing 4 aces from a deck of cards? Okay, so the answer is there are 4 aces in the whole deck. There are 52 cards in the whole deck, so the probability is 7.7%, or it's 0.077.